Welcome to the third lecture. I would like to start with a very brief revision of the last lecture. So what did we learn last lecture? We started with the addition of halogenohalides to alkenes, and we learned that this addition is a two-step reaction which proceeds over planar carbocation intermediate and is then followed to produce racemic halogenoalkane product. Moreover, we saw that if we use or if we add a halogenohalide to a terminal alkene, then we will only observe secondary halogenoalkane. And this is due to the so-called Markovnikov rule, and we saw that the addition of halogenohalides can therefore be regioselective. And finally, what we also saw is that we can have a so-called 1,2 hydride or even 1,2 methyl shift, and this shift then produces the more stable tertiary carbocation, and we will end up with tertiary halogenoalkanes as major products. And today we will start with the electrophilic addition reactions of alkenes, and here we will start with the addition of bromine. And first of all, you might wonder how the bromine can react as electrophile, because you would not expect to have a charge in this molecule. However, bromine becomes polarized if it approaches the carbon-carbon double bond. And then if this not polarized molecule comes nearer, and then the bromine, which is next to the carbon-carbon double bond, becomes electrophilic. Then in the first step, we have the addition of the bromine to the alkene. And here it is important that we see that there is no probability for one specific addition. That means bromine reacts equally with the top or bottom face of the carbon-carbon double bond. And then we can see that after this addition, then form a so-called bromonium ion intermediate. And this bromonium ion is a ring, and you can see already that we have now a 1-to-1 mixture of enantiomers. Then in the second step, we have attack of the negatively charged bromine to this bromonium ion ring. And the reason for this is that the positively charged bromine ion here in the ring has a very strong -I effect, and therefore the carbon atoms in the ring are electrophilic. And then the attack is preferred to this electrophilic carbon, and this is a very fast reaction step. And as we have a mixture of both enantiomers, we need to consider that this attack can be or will proceed from both sides, so that we end up again with a 1-to-1 mixture of both enantiomers. What is important now to remember is that we have two bromine atoms added to the opposite carbon-carbon faces in anti-addition. And also important, we have the bromonium ion as racemate and also the dibromide product as racemate. A strong evidence for the formation of a bromonium ion and the overall anti-addition of bromine to a carbon-carbon double bond is provided by the reaction of cyclic alkenes with bromine to produce cyclic 1,2 dibromides. This is due to the fact that in these compounds the rotation around the carbon-carbon bond where the bromine are now attached is not possible. That means the relative positions of the two bromine atoms in the products are fixed. And for example, if we have a look on the addition of bromine to a cyclopentene or a cyclohexene, we can see that we have the starting molecules, then we add the bromine, and we go over the cyclic bromonium ion intermediate, and then finally we end up with the enantiomers as products, and we can see that we always have 1,2-D bromide as racemate, which has the bromine atoms on opposite sides of the ring. And very important here is that we recognize, for example, here or here, that always the bromine atoms are either axial or equatorial, but never one axial or one equatorial. And this is then the proof for the so-called anti-addition. After the evidence of the anti-addition, we now want to understand what happens if we use substituted alkenes, because then the reaction will be stereospecific. And why this is the case, we can clarify by investigating what happens if we use the E-but2-ene or the Z-but2-ene. And here we can see that the formation of an intermediate bromonium ion explains why the addition of bromine to a substituted alkene is stereospecific. So in a stereospecific reaction, different stereoisomers of the reactant produce different stereoisomers of the product. And this is shown by the reaction of the bromine with this E and Z isomer. We can see here the intermediate bromonium ion, and then we see that we end up with different products. And very interesting is to see that the addition of bromine to the E isomer forms a meso compound, and this compound has a symmetry plane. In contrast, the addition of bromine to the Z isomer will form a racemate, and both the meso compound as well as the racemate are diastereomers. The E and Z isomers of but2-ene react to form different diastereomers of 2,3-D bromobutane, so we can say that the addition of bromine is stereospecific. And now it is important that we always choose the right starting material depending on the product we want to form. For example, if we would like to form the RR or SS enantiomers, this can only happen if we use the Z-alkene as starting material, but not if we choose the E-alkene. And this is very important. Now you can see the orange arrows, and here, if you want, you can train if you know how these different compounds relate to each other, and you will find the solutions in the slides.